So welcome back to my lectures on groups, rings and fields. Our next topic is on ring homomorphism and factor rings. Homomorphisms actually ring homomorphisms and factor rings. This is going to be our last topic in this entire course. We have defined very briefly what a ring homomorphism as an extension of group homomorphism. That is, if phi is a map from R to R prime, then this is a homomorphism if phi of A plus B is equal to phi of A plus phi of B, and phi of AB is equal to phi of A times phi of B. We have all defined this one for all A comma B in R. But in this section we are focusing on factor rings. Factor rings are very similar to factor groups. Actually, the idea is same. In fact, the elements of the factor rings are the same as the elements in the factor groups. They are left or right corsets. So the way we build the first factor group in group theory is like this. We defined a group homomorphism with a kernel H. Then we took the left or right cosets of H. By the way, H is a normal subgroup of G, and what we did is we took the left and right cosets, which are both are same, H or H, A plus H, or collections of all cosets, and we defined an operation like this: HA, H plus A plus H plus B is equal to H plus A plus B. With this operation, we found that this collection will become a group, and it is denoted by G over N and is called G over H is called the factor group of G over H. So we are going to use the same approach to build the first factor rings. By the way, this is actually we are building the factor group from homomorphism, and this becomes a normal subgroup of G. But we don't need to have a homomorphism to define a factor group. If you take any subgroup of G which is normal in G, still the collection of all left or right cosets of H will form a group with the similar binary operation as in kernel of phi. Right? And this is called G over H. So we don't need to have a homomorphism to define a factor group. So similarly, what we are going to do in ring, we are going to extend this idea to rings. So we'll start with the ring homomorphism. Then kernel is same. With kernel is actually the kernel of R as a group. With kernel is equal to H. Then R over N is a factor group. Now we want to extend this one to factor ring. Factor group means you have only one binary operation, that is actually addition. Just like this. But if you want to extend to a factor ring, we need to have one more binary operation. So multiplication needs to be defined on R over N. Sorry, this is actually, I'm going to take it as N, okay? R over N. But for first, what we'll do is first we'll show that if you are constructing a factor group from a homomorphism, the multiplication what we are going to define is well defined, and also R by N is associative on the multiplication, and it is also distributive on, but the multiplication is distributive on the addition of R over N. So that is the first part. So what we need to do is define a multiplication on R over N. Then we need to show that it is well defined. Then we need to show that associativity is valid for this multiplication, or multiplication is associative. Then we need to show that multiplication is distributive over addition. That is the first part. That is when we are defining the factor group based on a ring homomorphism. Then see here, if you want to build a factor group from any subgroup, that subgroup needs to be a normal subgroup. If H is not normal, left coset, the collection of left cosets and the collection of right cosets won't match, and we cannot define an addition here. So that is a condition on any subgroup. Similarly, if you take any subring of R, we need to find the condition for which the multiplication is defined well and it follows the ring axioms. So that is the plan of this topic. Now, before we come to building the factor groups for factor rings, let us look at the the properties of ring homomorphism. Let us start with a group homomorphism. Properties of homomorphisms. Group. We have done this earlier, but I just want to revisit these properties of group homomorphism. Phi is a homomorphism from G to G prime, then phi 0 is equal to is the identity of G prime, then phi of minus A is minus phi of A. Then if H is a subgroup of G, then actually phi 0 is the identity of, to be very precise, let us say phi of G, which is same as G prime. If H is a subgroup of G, then phi of H is a subgroup of phi of G. Then if K prime is a subgroup of G prime, then phi inverse of K inverse K prime is a subgroup of G. These are the properties of group homomorphism. So when it comes to ring, these are all, the first two are 1, 2, 3, 4. First two are all the properties of a group, which is always true in ring. But when you want to extend this to multiplication, what we will do is here, see for every, so let us consider a homomorphism R to R prime be a ring homomorphism. But this R doesn't need to have a identity, multiplicative identity. Of course it has the additive identity. This is the additive identity, so this is always true here. I am extending this idea to multiplication. So if R has a multiplicative identity, that means unity, R is a ring with a unity, then R prime also has a multiplicative identity, that is unity, and 1 prime is equal to phi of 1. 1 prime is the identity of, multiplicative identity of R prime, and 1 is the multiplicative identity of R. And the second one, the inverse. So this is the property corresponding to the additive property here. Okay, so this in ring homomorphism, R, if you consider R as a group, these two are valid here. This is on top of these two properties. So this is not an extension of this, but this is an addition to these properties. So here, second property corresponding to this, you can add one more property for the multiplication, and that is phi of A inverse is equal to phi of A inverse if A is a unit, meaning if A has a multiplicative inverse. R doesn't need to have multiplicative inverse for all elements in R? If it has, this is what happens, where A belongs to R. Third, if you are extending 3 and 4, if S is a subring of R, so is phi of S as a subring of phi of R. If S prime is a subring of R prime, so is F inverse of S prime as a subring of R. So these are the corresponding ring properties of the homomorphism. Let us briefly prove these results. So the first property is, let 1 be the multiplicative identity of R. That implies for all A in R, A times 1 is equal to A. So phi of A times 1 is equal to phi of A for all A. R is a ring homomorphism, so this is phi of A times phi of 1 is equal to phi of A, and that implies phi of 1 is the unit of phi of R. So unity of phi of R, or multiplicative inverse, multiplicative identity. This is same as multiplicative identity. The inverse of A is the image of the inverse is the inverse of the image. So let A be a unit, meaning it has a multiplicative inverse, and that implies A inverse X, and that implies A times A inverse is equal to 1, and that implies phi of A times phi of A inverse is equal to phi of 1, and this is equal to 1 prime, and which implies that phi of A inverse is equal to phi of A inverse. Right? For a unit, which means that if a unit is mapped to another unit in R prime, and its inverse will be the inverse of the map. The next property is a subring. All we need to prove here is that the phi of S is closed under multiplication, because it's already a subgroup. So all we need to show is that if you take two elements from phi of S, its product is also in phi of S. Then we are done with this. So assume that S1 prime comma S2 prime belongs to phi of S, and that implies there exists S1 and S2 in S such that phi of S1 is equal to S1 prime, phi of S2 is equal to S2 prime, and that implies phi of S1 times S2 is equal to phi of S1 times phi of S2 is equal to S1 prime times S2 prime, because S1 times S2 belongs to S, because S is a subring, that implies phi of S1 times S2 belongs to phi of S, and that implies S1 prime times S2 prime belongs to phi of S, and that implies phi of S is closed under multiplication, and that implies phi of S is a subring of phi of R. The last part I am going to leave it to you as an exercise. The proof goes very similar to this, so I am not going to do it here. Now the kernel of a ring homomorphism, let's say phi from R to R prime be a ring homomorphism. So the kernel of phi is same as the kernel of phi as a group homomorphism. Okay, so kernel of phi is defined as elements from R such that phi of R is equal to the additive identity of R prime. Okay, this is exactly same as the group. Okay, now phi is 1 1 if and only if kernel of phi is equal to the trivial subgroup of R. This is actually subgroup, not subring. Okay, so the kernel is only a group property. It is not a part of the ring homomorphism. It's a group homomorphism. And if you take an element from A, R, let us say let A belongs to R, then phi inverse of phi of A is the left coset of the kernel. This is also a property coming from group theory. Okay, if phi is a group homomorphism, then phi inverse of phi A is the collection of all elements that are mapped to phi A. See, actually phi inverse of phi A is equal to G belongs to G such that phi of G is equal to phi of A. So that is actually that will be equal to H plus A, or A plus H, because H is normal. Well, where H is equal to kernel of phi. Now we are ready to define our first factor ring. So first factor ring we are going to define from a factor homomorphism, from a ring homomorphism, just like we did it in group theory. First group, factor group, is built from group homomorphism. So similarly, let us start with a ring homomorphism. Let phi from R to R prime be a ring homomorphism. With n is equal to kernel of phi. So then clearly R by n is a factor group. Now we need to define, so this is actually R by n is the collection of right or left cosets, right? So this is a factor group with addition defined as, these are the elements, so n plus a plus n plus b is equal to n plus a plus b. So we are going to, we want to make this as a factor ring. So we need to define another binary operation with the same element. So define multiplication on R over n by n plus a times n plus b is equal to n plus a. Now what we need to prove that this binary operation is well defined. That is the first part. Then we need to prove that multiplication is associative. Then we need to prove that multiplication is distributive over addition. And that implies R by n is a ring called factor ring. That is the first factor ring we are going to build. And later on we will come back and see if we can put any condition on n. We will remove this homomorphism. We will take any subring and see what are the conditions we need to impose on that subring for us to create a factor ring in a general setup. So let us start with this. So this we need to prove that this is a well-defined binary operation. So in order to prove that it's a binary operation, what we do is, this is actually a coset, this is a coset, and this is a coset. So we will take a representative of this coset, we will take another representative of this coset and see that that representative falls into this one. So let n1 comma n2 belongs to n, and that implies n1 plus a times n2 plus a, n2 plus b is equal to, we are multiplying these two with the representative from n, and a and b are representative of this coset and this coset, and this implies n1 n2 plus n1b plus an2 plus ab. n1 comma n2 belongs to n implies phi of n1 is equal to phi of n2 is equal to 0, because this is the kernel. So that implies phi of n1b is equal to phi of n1 times phi of b, and this is actually 0 prime. So this is actually 0 prime, so this will be 0. Similarly, phi of a n2 is equal to 0. So that implies n1 plus a times n2 plus b is equal to n plus ab for n is equal to for some n belongs to n, because phi of n1 n2 plus n1b plus a n2 is equal to 0 implies n1 n2 plus n1b plus a n2 belongs to n, and this is our n. So that implies if you take a representative from here, take another representative from here, when you multiply it, you get another representative from here, and that implies n plus a times n plus b is equal to n plus ab. So this is a well-defined binary operation, no problem. It's a well-defined binary operation on the cosets of the kernel. Now we need to show that it is associative, which is very, very simple, meaning n plus a times n plus b times n plus c is equal to this. If you multiply this, actually n plus ab times n plus c, and that is equal to n plus abc, and that is equal to n plus abc, because a, b and c are coming from R. So we are going to write for all a comma b comma c belongs to R. Okay, so this actually implies n plus a times n plus b times n plus c, and that implies multiplication associative. Now this multiplication is distributive over addition. That means n of n plus a times n plus b plus n plus c is equal to n plus a times n plus b plus c, and that is equal to n plus a times b plus c. And because these three are from R, this is actually distributive. So this means n plus ab plus ac, and that is equal to n plus a times n plus b plus n plus a times n plus c. So that completes the proof of the fact that R by n is really a ring, and that's called factoring. I want to make sure that when phi is a ring homomorphism with a kernel phi is equal to m, what we have done is we showed that the factor we showed that the collection of all left or right cossets of n is a factor ring. Is the factor ring, right? But we never mentioned about this n. N is actually definitely is a normal subgroup of of R. But it is also a subring of R, because all we need to show that if you take two elements from here, that is closed under multiplication. So let A comma B belongs to R, and that implies phi of A times phi of B is equal to 0, and that implies phi of AB is equal to 0, and that implies AB belongs to N, and that implies N is a subring of R. The reason why I pointed out this one here is, though we started with a ring homomorphism and building the factor ring based on the kernel, that kernel is really a subring. Okay, so we are actually building the factor ring from a subring. In this case, it happened to be the kernel of the homomorphism. So when you want to generalize this, instead of a kernel of a homomorphism, we are going to assume that N is a subring of R, and find out a condition on N where the multiplication is well defined. See, the group part is already done, because R is a commutative group or abelian group under addition. So it is every subring of R is a normal subgroup of R. So our next attempt is to take a general subring, impose some conditions on N so that N plus A times N plus B is equal to N plus AB is well defined. If you put some conditions on N such that this is always true, then we are generalizing the idea of factoring to a subring instead of a kernel. Just like we did for factor groups. In factor groups, we started with kernel, and later we say that you take any subgroup of G if it is normal, then G over N is well defined. This is the condition we put on this any subgroup. Similarly, we are going to put some condition on N where N is a subring of R, so that this multiplication is well defined. So our next step is to enforce some conditions on a subring so that the multiplication is well defined. So that is our next step. So let N be a subring of R. Then the multiplication N plus A, N plus B is equal to N plus AB is well defined if and only if A n1 belongs to n and n2b belongs to n for all A, B in R and n1, n2 in n. In other words, Na is contained in n and Bn is contained in same An. Let us make this as An and this is Nb for all AB in R. Okay? So if these conditions are satisfied, this is well defined. And if this is well defined, these conditions are satisfied. So let us assume that An1 belongs to n, b, n2b belongs to n for all AB in R and n1, n2 in n. Now we'll so what we can do is we'll take a representative of this and a representative of this. See that you get the representative of this. So n1 plus A times n2 plus B is equal to n1 n2 plus n2B plus A n2 plus AB. This definitely belongs to n. This also definitely belongs to n because of this. This is n1. This also belongs to n because of this condition. So all these are in n. Right? So this actually can be written as n plus AB for some n in n. Actually where n is equal to n1 n2 plus n2b plus an1. So if this is true, the multiplication is well defined. That implies n plus a times n plus b is equal to n plus ab is well defined. Now let n plus a n plus b is equal to n plus ab is well defined. We need to prove that these two conditions are satisfied. So what we will do is, for all A and B in R, so we will take B is equal to 0. So what this will become n plus A times n is equal to n plus A times 0, and that is equal to n. Right? Now what we will do is, so n plus A times x is equal to n. What we will do is, we will take A from here. A belongs to n plus A, definitely. And we will take n1 from here. So that means A times n1 belongs to because it has to come from n. And that means, so that is exactly what we need to prove. If you take, see, A belongs to n plus A, definitely, and we'll take one element from n. Okay. Similarly, n to B belongs to n. What we'll do is we switch A and B. So we'll have n times n plus B is equal to n. Then we replace n plus A by B, and in n we'll take n2. So n2B is equal to n. So this implies if n plus A times n plus B is equal to n plus AB, then AN1 belongs to n and n2B belongs to n for all n1, n2 in n and A comma B in R. So this calls for a new definition. Let n be a subring of R such that NA is contained in n and Bn is contained in n, then n is called an ideal. It's a very important structure in ring theory. So n is a subring of R, then R by n is a factor ring if and only if n is a ideal. Just like the normal subgroup, if H is a subgroup of G, then G by H is a factor group if and only if H is a normal subgroup. Okay?